In 2019, scientists changed the definition of temperature, electric current, and the matter itself. Yet nothing in the lab actually changed. No measurement shifted. They didn't change reality. They changed who holds the ruler. The old platinum kilogram was retired, replaced by glowing constants. The puzzle, how do you build a unit out of a number you simply decide to freeze? So how does this trick work? Every one of these units follows the same three-step recipe. Step 1. Choose a constant of nature. Step 2. Declare its numerical value exact forever. A defining constant is a number we freeze by decision. Step 3. Invert the relationship to extract the unit. The unit becomes whatever makes that frozen number true. 4 units run through this pipeline. The elementary charge gives the ampere. The Boltzmann constant gives the kelvin. The Avogadro constant gives the mole. And the luminous efficacy gives the candela. Start with the ampere, the unit of electric current. We fix the elementary charge, E, the charge of a single proton, at exactly 1.602176634 times 10 to the minus 19th coulombs. A coulomb is just an ampere times a second, so E equals that number in ampere seconds. Now invert and solve for the ampere. 1 ampere equals E divided by 1.602176634 times 10 to the minus 19th, all divided by the second. The second itself comes from the cesium frequency. Delta nu cesium, fixed at 9,192,631,770 oscillations. Divide the two frozen numbers and the 1 ampere equals 6.789687 times 10 to the 8th times E times delta nu cesium. Now the easiest case, the mole. We fix the Avogadro constant at 6.02214076 times 10 to the 23rd per mole. 1 mole is simply that many things: atoms, molecules, ions, electrons. So 1 mole equals 6.02214076 times 10 to the 23rd times 1 over the Avogadro constant. Watch what happens. The Avogadro constant carries units of 1 per mole, so 1 over it has units of moles. Multiplying the pure count by that gives back exactly 1 mole. No kilograms, no seconds, pure counting. The ampere and the mole were the easy cases. The kelvin and the candela hide an extra layer. Take the kelvin, the unit of thermodynamic temperature. We fix the Boltzmann constant, K, which links temperature to energy, at exactly 1.380649 times 10 to the minus 23rd joules per Kelvin. Here's the catch. The joule isn't fundamental. A joule unpacks into kilogram times meter squared per second squared. So the Kelvin inherits 3 definitions. The kilogram, which comes from the Planck constant h, the meter, which comes from the speed of light, and the second from delta nu cesium. Substitute all of them. The kilogram times meter squared per second squared collapses into h times delta nu cesium. After the dust settles, 1 Kelvin equals 2.266665265 times h times delta nu cesium divided by K. What does 1 Kelvin physically mean? The Boltzmann constant converts a temperature into a thermal energy, simply K times T. So 1 Kelvin is the temperature change that shifts thermal energy by exactly K joules, that is 1.380649 times 10 to the minus 23rd joules. Temperature stops being about thermometers and the mercury. It becomes a direct statement about energy per degree. The candela is the most human unit of all. It measures luminous intensity, brightness, as the eye perceives it. We fix the luminous efficacy, KCD, at exactly 683 candela steradian per watt. That value is calibrated to the average human eye looking at green light at 540 times 10 to the 12th hertz, the color we see most efficiently. The steradian measures solid angle light spreading through a cone. Now invert the relationship. The watt hides inside kcd, and the watt is energy per second, which again breaks down into kilograms, meters, and seconds. Substitute those mechanical units and the Planck constant h and delta new cesium appear once more. Working through the arithmetic, 1 over 683 divided by 9,192,631,770 squared times 1 over Planck's constant gives a factor of about 2.6 times 10 to the 10th. So 1 candela equals 2.614830 times 10 to the 10th times kcd times h times delta new cesium squared. Why do Kelvin and candela drag in h and delta new cesium, but the mole doesn't? Compare them directly. The ampere fixes E, carries no mechanical units, and stays clean. The mole fixes the Avogadro constant, a pure count, the cleanest of all. But the Kelvin fixes the Boltzmann constant, which carries the joule and energy. And the candela fixes luminous efficacy, which carries the watt, a power. Energy and power are mechanical. They must be traced back to mass, length, and time. That tracing is exactly what pulls in the Planck constant and the cesium frequency. 3 confusions worth clearing. First, the redefinition did not change the size of a Kelvin or an ampere. The values were chosen so the new units match the old ones within measurement uncertainty. The definitions changed, the magnitudes did not. Second, a mole is not a unit of mass. It counts entities, divorced from the kilogram, since 2019. Third, fixing a constant isn't circular. It's a deliberate choice of anchor. We freeze the number and the unit becomes whatever makes that number true. Step back and a single picture emerges from all this algebra. 7 defining constants form a central ring. Delta nu cesium, the speed of light, the Planck constant, the elementary charge, the Boltzmann constant, the Avogadro constant, and the luminous efficacy. From them radiate all 7 base units, the second, meter, kilogram, ampere, Kelvin, mole, and candela. The ampere traces to E and the delta nu cesium, the Kelvin to kh and the delta nu cesium, the mole to the Avogadro constant alone, the candela to luminous efficacy, h and the delta nu cesium. Every unit anchored to constants believed invariant across all space and time. An alien civilization or a lab in the year 3000 could reconstruct our exact units from physics alone. The 2019 redefinition was the culmination of a 150-year project to remove every last physical artifact from measurement. 7 numbers, frozen forever, holding up the entire system of human measurement.